Hi, my name is I-Hsiang Wang. I'm a PhD candidate at UC Berkeley, and my advisor is Professor David Shea. This poster covers part of my thesis work. The topic is cooperative interference management. Nowadays, interference has become a major factor that limits performance in wireless networks. Traditionally, radios in a network have to deal with interference on their own, since people used to view them as isolated nodes. In many scenarios, however, cooperation among radios can be induced, and they are no longer isolated. For example, in cellular networks, cooperation among base stations can be enabled via infrastructure backhaul networks. It is a common belief that cooperation among radios can help manage interference by forming distributed MIMO systems. It is also a common misconception that they can cooperate in an unlimited manner. In most scenarios, however, they cannot, and the rate at which they can cooperate is limited due to various physical constraints. In this work, we explore theoretical and practical aspects of interference management with limited cooperation among radios. So we first study the two-user Gaussian interference channel with limited receiver cooperation and limited transmitter cooperation. We give the first uniform approximation result on the capacitor regions of these two channel models, and therefore we understand how much interference can limited cooperation mitigate in these two canonical settings. By characterizing the capacitor region within a constant gap, regardless of channel parameters, we accordingly identify the gain from limited cooperation both qualitatively and quantitatively. We also observe an interesting uplink-downlink reciprocity between the system with limited receiver cooperation and the system with limited transmitter cooperation. So for the qualitative part, we identify two regions regarding the gain from limited cooperation: the linear region and the saturation region. In the linear region, the cooperation is efficient in the sense that the growth of user data rate is roughly linear with respect to the cooperation rate. The gain here is merely a degrees of freedom gain provided by the distributed MIMO system. In the saturation region, on the other hand, cooperation is inefficient in the sense that the growth of user data rate becomes saturated as one increases the cooperation rate. The gain here is just a power gain of at most a constant number of bits, and the constant is independent of how large the cooperation rate is. Therefore, we focus on the linear region, and we find that it is either one cooperation bit buys one more bit, or two cooperation bits by one more bit until saturation. And the behavior depends on the channel parameters. So throughout the inferential theoretical analysis, we propose good strategies for receiver cooperation and transmitter cooperation. Next, we aim to implement these proposed schemes. As a first step, we aim to implement an important module in receiver cooperation. This module is called quantized map and forward relaying scheme. For that purpose, we look at a simpler model with single source, single relay, and single destination. We propose a modulation encoding framework involving bit interleaved coding modulation and low-density graph-based codes. We use a LDPC code as a source for encoding, and we use a simple scalar quantizer at the relay, and we use a LDGM code for mapping at the relay. At the destination, we derive a joint decoder, based on the factor graph, and we give the low complexity message passing algorithm. We also show that these analytical tools, such as density evolution in the point-to-point case, can be extended to this framework. That's roughly what my poster covers. For more details, please go to my website, which can also be linked from the ITA website. Thank you.